Welcome to Ask and Learn.
All right, guys, we're going to be doing problem 106, chapter 5, a chemistry central science. Okay, so a coffee cup calorimeter, you can see this in figure 5.18 of your textbook, contains 150 grams of water at 25.1 degrees Celsius. Now, a 121 gram block of copper is heated to 100.4 degrees Celsius by putting in a beaker of boiling water. The specific heat of copper is 0.385 joules per gram Kelvin. We don't have to convert from Kelvin to Celsius because the delta T for Celsius is equivalent to delta T for Kelvin. The copper is added to the calorimeter, and after a time, the contents reach a constant temperature of 30.1 degrees Celsius. Determine the amount of heat in joules lost by the copper block. So this is going to be part A. So we're going to use Q equals MC delta T. Q Cu is going to be equal to 121 grams times 0.385 joules as joules per gram Kelvin. Times the difference in temperature, which is going to be a negative 70.33 degrees Celsius, because remember, going from a high temperature to low temperature. So QCU, that's going to equal 3,275 joules. So now we're going to find the amount of heat gained by the water. So let me reiterate, it's a negative 3,275 joules. That's what's lost by the copper. So QH2O is equal to 150 grams. Zero times 4.18 8 times delta T, which is going to be 5 degrees Celsius. So QH2O that's going to be 3,135 joules. So that's the answer of part B. Part C, we're going to notice that the difference between your answer part A and B is due to the heat loss due to styrofoam cups and the heat necessary to raise temperature of the inner wall of the apparatus. The heat capacity of the calorimeter is the amount of heat necessary to raise temperature of the apparatus, which would be the cups and the stopper, by 1 Kelvin. They want us to calculate the heat capacity of the calorimeter in joules per Kelvin. Ideally, if you have perfect heat transfer, the heat lost by your copper is going to equal the heat gained by your water, but that we don't live in that ideal scenario. So let's get a new page. C. So let's bring our numbers over here. QH2O is going to be 3,135 joules, and now Q copper upper, which is going to be 3,275 joules. Now, the delta T in this case, we're going to only focus on the amount of actual temperature increase of the water, which is going to be 5 degrees Celsius. Because the water is since our calorimeter is filled with water, that's the medium we're focusing on. So now this is actually very simple. So we're going to have 3,275 minus 3,135 joules. We don't have to care about the sign. We just need to make it positive because as we can make it positive because we just care about the difference between these two magnitudes. So 5 degrees Celsius is also equal to 5 degrees Kelvin. And so our answer to this is going to be 28 joules per Kelvin. And that's the heat capacity of our calorimeter. So now we're going to go to another page. Okay, for part D, they want to know what would be the heat capacity. What would be the final temperature of the system if all the heat lost by the copper block were absorbed by the water in the calorimeter, which is assuming like perfect transfer. So we're going to. So in this scenario, we would have like perfect transfer. Delta Q of U is going to equal Q of H2O. This is assuming perfect heat transfer. So now we can solve for we know T initial in this case is for both these samples. So now we can find that now we can look at the final temperature, which is going to be our new final temperature. So we do Q equals MC delta T. So we're going to have negative 121.00 grams. In fact, to save space, let's not use the units. 0.385. And we're going to multiply this by delta T, because Q equals MC delta T. But let's just change this to T minus Ti. Ti is going to be the initial for both water and copper, and T is just going to be our new final temperature. So for copper, our initial temperature, remember, that is going to be 100.4 degrees Celsius. Now for water, we're going to have 150 grams of water. 0 times 4.18. And then we're going to have T minus 25.1. Now we plug everything into our calculator. So 121 times 0.385. So that's going to be minus 46.599. Then we're going to S9, and we have our variable T here. Then we're going to add, because if you have a negative and negative, it cancels out. That's plus 46.7. 4,677, which is going to equal 627t minus that's 15,777, 737. As in, my apologies. So now we're going to be doing some algebra. So we have, so we subtract. So we're going to have both our t's on one side and both our constants on the other. So subtract. So as add 15,737 to the left and add 46.59 to the right. Right. So then we have an issue of 673.59. T is going to be equal to 15,737 plus 46.59. So you're going to have 15,783.59. Sorry, sorry, wrong calculation. 4,677 plus 15,737. That's going to equal 20,414. So now we divide both sides by t. Sorry, we divide both sides and isolate t. So 2,414 divided by 673.59. That's going to give us a t value of 30.3 degrees Celsius. So this is going to be the final volume we would get if we are. So this is going to be the final volume that we're going to get at if if all of the heat from the copper was transferred to the water. And you'll notice that the change in T final is not that different. Over here we had a T final of 30.1, and over here we had 30.3. That's because the actual difference between between the heat of the water and the heat of the copper actually isn't that different. It's less than it's a fraction. It's less than 10%, so it's a very small fraction that's actually lost the calorimeter, but it does cause this difference.